Okay, so we took a look at the variance and then the covariance. So the covariance is measuring how two sets of data vary, and I'll say covary. Notice that this is ordered so that you're comparing like x1 to y1, then x2 to y2, x3 to y3, and so on. Okay, um, so by the way, just before we leave this covariance computation, notice that if you had two vectors x and y, right, then you could actually do this as a dot product. So sxy squared you could write as 1 over m minus 1 times the vector x minus x bar dotted with y minus y bar. Okay, so that is a dot product between two vectors, or if your vector was already mean subtracted, right, you could simplify that so it's just x dot y. Good. I mention this is because you might remember that there is a certain way of looking at the dot product, right? And so from linear algebra, you might recall that x dot y is equal to the norm of x, norm of y, cosine theta, right? Do you remember that? And so this is my vector x, vector y. So in this case, I want to interpret what these things are. So this is a this is a vector with data in it, right? Oops. Let me rewrite that. And this is a vector with data in it. And I'm assuming that these have mean 0 already. Good. Now what does the norm of x represent? The norm of x, that's the sum of xi squared, right? And then you take the square root of that. Does that look familiar? So if I'm assuming again that the vector in x has 0 mean, so this is actually the standard deviation of x, or you could write s of x. Similarly, the norm of y is the square root of the sum of yi squared, and so if this is already mean 0, right, then this would be the standard deviation of y, right? And so getting back to my discussion here, the cosine of theta I can write as x dot y over the magnitude of x, magnitude of y, or standard deviation of x, standard deviation y. And that actually has a name, and that name is the correlation coefficient. So rxy is equal to sxy squared. That's the that's the covariance divided by the standard deviation with x, standard deviation with y. And so let's go ahead and compute that out. Right, that's going to be the sum. Oh, you can fill that in. I want to use the matrix or the vector form of this instead, because this is equal to 1 over m minus 1 times x dotted with y, right, divided by, well, this is x dot x, square root of x dot x, 1 over the square root. Well, if I take x dot y, maybe I'll do it this way. The norm of x, norm of y multiplied together, right, you're going to have, oops, ooh, I better be careful here. This is not the standard deviation, right? I have to divide by m minus 1. So let me write that. Sorry about that. Let me write it this way. S sub x is equal to 1 over m minus 1 square root times the magnitude of x, like this. There we go. Now I'm getting the notation that I need. Good. And now I'll fill this in up here. So multiply those two together and you just get m minus 1. M minus 1's cancel. Good. That's what I wanted. And that is equal to the cosine of theta. Whew. So therefore, we know all about the correlation coefficient, because the correlation coefficient can only be a number between -1 and 1. So think of the correlation as being perfectly negatively correlated if the cosine of theta is -1, and perfectly correlated if the correlation coefficient is equal to +1. And then we say that x and y are uncorrelated if x dot y, let me not say that, if rxy equals 0. But then using our notation here, right, you can see when is rxy equal to 0? That's when x dot y is equal to 0. And so uncorrelated means that the data as vectors is orthogonal. Uncorrelated data vectors means that the vectors are orthogonal. Good. And so that's a really important point. Sometimes we don't see that because it's not a easy thing to visualize right off, but the linear algebra notation, I think, makes it really clear. Good. Now let's see. So when are two sets correlated? So when do you get a perfect correlation? You get a perfect correlation when your y is, maybe I'll think about it a different way. If x and y are linearly related. So for example, suppose I've got a set of data x, and then I take my data y to be mx plus b. So mx1 plus b, mx2 plus b, mxn plus b. Then the correlation between these two is going to be equal to +1 if the slope is 1, -1 if the slope is negative. And you'll show that in the homework. I don't want to give that away. But notice, of course, that these aren't mean zero yet. We'd have to mean subtract. And so our notation gets a little funky when we do that. But now it is true that uncorrelated does not necessarily mean that there's no relationship between the two vectors. So uncorrelated does not mean no relationship between the data sets. Okay, and so what do I mean by that? That's because our measure of uncorrelated is only looking at linear relationships, not nonlinear relationships. So here's an example of what I mean by that. Suppose that you have some values of t. Say, t is some numbers, -2, -1, 0, 1, 2. You can take as many as you like. Let x be equal to cosine of t, and y be equal to the sine of t. Then, it's not clear from here, but x and y are uncorrelated. But as we know from our trig, if I take the square of each of the elements of x and add it to the square of each of the elements of y, I get 1. Therefore, there is a perfect relationship between x and y, but it's not a linear one, it's a nonlinear relationship. And so in this case, we see again x and y are uncorrelated. We're going to check this in our computer, but then x squared plus y squared equals 1. So there is a relationship between the two. So uncorrelated does not mean that there's no relationship. It means that there's no linear relationship. Okay, that's going to be important when we're looking at nonlinear data in a little bit. Good. Okay, geez, the time just runs by really fast. So the last video we're going to do in this little stats section is to talk about the covariance matrix, because that's going to be a really important idea coming up.